Two more authors were added, so that is why this number has been revised from what Tarun showed you earlier to 39 from the same 9 Indian institutions. In this talk, what I'll strive to do is the following. First, I'll communicate some of the surprises these two detections of gravitational waves have brought forth. And I'll use that as a context to introduce what specific contributions were made to these discoveries by Indian scientists. I'll not be able to cover the full spectrum, but that's also planned because I have other colleagues later in this session who will communicate those to you. One thing I would like to emphasize is that the detection of gravitational waves is expected to remain a low signal to noise ratio endeavor for years to come, which is why it's important that we understand the instrument and the type of noise it is affected by, and find ways of discriminating that noise characteristic from the details of signals, which it would be helpful if we can predict using Einstein's equations. And a lot of effort was invested in this, not only by Indian scientists, but also their foreign collaborators. Finally, something that Tarun brought up earlier, it is important to keep in mind that this enterprise of gravitational wave detections is a multidisciplinary one. It involves not only scientists from various areas of physics and mathematics, but also and astronomy, but also engineering. I'll perhaps have a chance to give a couple of illustrations of this interdisciplinary nature of this endeavor. So beginning with the discovery, which was made on September 14th, 2015, and announced on February 11th. What the two LIGO detectors at Hanford and Livingston found was a gravitational wave signal which was emitted by a binary black hole system, comprising a black hole with a mass of something like 36 times the mass of Sun, and another secondary black hole with a mass of about 29 times the mass of Sun. These two objects, we captured them in the last 10 cycles or so before merger. And of course, after they collided, they formed a heavier black hole with a mass of about 62 times the mass of Sun. If you do the math, you realize that there is a gap of about 3 times the mass of Sun. And so according to Einstein's equation, the prediction is that that mass was emitted in the form of gravitational wave radiation. So all of that mass was converted into energy. Some of that energy was captured by these LIGO detectors, about 1.3 billion light years away from the source. This was a better than 5 sigma event, which translates to a false alarm rate of something like 1 noise false alarm per more than 200,000 years. And that essentially means that if you have a coin with a head and tail, right, if you toss it 22 times, you get head every time consecutively. So in other words, it's highly unlikely that noise would produce such a concurrent detection across these well-separated detectors, separated by about 3,000 kilometers. And yeah, it did capture the public imagination because this cartoon came out, I think, in the newspapers produced by Amul within a couple of days of the announcement. But in seriousness, it took a lot of effort to make this happen. Okay, this is not my laptop, so something popped up. What I'm going to try and show you is an animation which was produced by solving Einstein's equations. Is there a way to run this? Simulating extreme space-time group comprising multiple universities in the world, where the two black holes are being represented by beam splitter and the mirrors. They are coupled in more than one way. The ground is a coupler because these mirrors are all suspended from some suspensions which are pinned to the ground. But then the laser beam itself is another coupler. So there are many ways in which these different components can couple in a nonlinear way, in the sense that ultimately the length sensing is proportional to a higher order of the amplitudes of these different elements. And when there is nonlinear coupling, of course, in addition to the harmonics, you can also have excess noise in sidebands. So there could be a 10 hertz bounce mode of a mirror that can couple with say, the violin mode of the string of the n-test match suspension, which is at 500 hertz, to create sidebands, plus minus 10 hertz sidebands, or even 4 hertz sideband, which is another excitation frequency of, so there's bounce mode. Okay, I don't show the 4 hertz here, but there is actually a 4 hertz mode too, which is related to one of the resonances of the suspensions of these mirrors. So all of these noise sources were in fact found, studied, and accounted for before we could announce this detection. And that is why that was one of the reasons it took time after observing it in September 14 and then announcing it on February 11. And remember the transient nature of the signal, 1/5 of a second. Some of these excess noise sources which are showing up on this bicoherence plot, which helps us track frequency versus frequency coupling. So it's a higher order statistic tool. These couplings can show up on these plots, and there also you notice the timescales are of the order of a fraction of a second. But these tools, which were actually developed to study noise, are useful also to study nonlinear coupling, for example, in two neutron stars as they merge, because there also you have multiple timescales. One is the orbital timescale of these two neutron stars as they are coalescing, and the other timescale is set by the equation of state of the neutron star, how stiff it is, or resisting collapse, or how soft it is, or allowing collapse. And those can also create multiple frequencies, which we are actually going after in another activity in one of my groups. Bala talked about the importance of the match filtering technique, which was used, but I'm running out of time, so I'm not going to spend much time on this. But along with that, multi-detector statistic that was used was also something that was developed with my collaborators. This is the details of the second detection on 26 December 2015. Here, the signal was weaker, so weak that it's well embedded in noise, and here, match filtering technique was critical, and the unmodeled search pipeline, which was instrumental in the first case, could not find this with significant enough signal. So that was the first confirmed detection. This is the second. This is the third one. You saw this in Tarun's slides, so I'll skip forward. I'm out of time, so I'm not going to. Well, what I'll say is that here is another simulation, but that may not work. But basically, if you see a neutron star orbit and fall into a black hole, before it does so, you will notice that it gets tidally disrupted. Now, why is that interesting? When it gets tidally disrupted, it decompresses the neutrons in the star, which means that they become fissile. Basically, our process nucleosynthesis can happen, and you can get radiation. In fact, such radiation has been characterized as a kilonova by astronomers, and there have been claims of 1 or 2 detections of kilonovae. But once again, if we can simultaneously or concurrently see an electromagnetic signal like that with a gravitational signal from the inspiral, then that will be a smoking gun that indeed these mergers produce both kinds of signals. So again, because of lack of time, let me just fast forward to my penultimate slide. Here, what I'm showing is the large sky error region that the 2 LIGO detectors are giving us for the location of these sources. So that is the one associated with the first discovery. Varun is going to talk more about it, but the challenge this produces for us is the following. The telescope field of view typically is less than of the order of 1 square degree, whereas this arc has a patch area of something like 600 square degrees. So you cannot scan all of this in one night. So how do you go about this while battling the problem of setting of the patch? Because of course, the Earth is spinning. So there are some high probability tiles for finding the electromagnetic counterpart, but then there are other tiles which are begging for your attention because they're going to set sooner. So how do you sequence or schedule these, the telescope pointing? It may look like a traveling salesman problem, but it is not. We found an optimal solution, but after the referee demonstrated us to find an algorithm that was perhaps already found by computer scientists, we did some digging and found that they came very close. And there is a problem known as the maximum weight matching problem, which comes very close to this problem. But we do have an optimal scheduler to actually track these different tiles in the sky. With that, I come to the last slide. So in summary, Indian scientists collaborated with their LSE colleagues to detect and characterize these 2 discovery signals. Searching for an electromagnetic counterpart was difficult. We have not found any, maybe because these are binary black holes, but the patches are very large. LIGO India can solve that problem, along with perhaps Kagra in Japan and Virgo in Europe. And this project, LIGO India, is moving ahead. Coincident gravitational wave and electromagnetic observations hold out the promise of interesting new discoveries, but maybe foremost of them would be phenomena that we have not conceived so far yet. Thank you for your attention.